It's my pleasure to introduce an inspiring speaker who represents the future of cybersecurity in the automotive world. So please join me in welcoming Iwinosa. She is a third-year Ph.D. student in computer engineering at Clemson University. She is working with the VIPR-GS Center in partnership with the U.S. Army. Iwinosa's research focuses on securing connected and autonomous vehicles, particularly in areas such as over-the-air updates, software supply chain protection, blockchain, and privacy. She is a committed member of Women in Cybersecurity in the U.S. She mentors underrepresented students, leads workshops, and advocates for gender diversity in STEM as a graduate ambassador. Whether she's presenting at the conference or educating future professionals, Iwinosa is driven by a powerful mission to develop secure, scalable solutions for the automotive industry while empowering the next generation of women in technology. So please give a warm welcome to Iwinosa Aideyan. I go backstage and I let you share your screen.
Okay, thank you for that amazing introduction. I really appreciate that. I'm so happy to be here this morning or afternoon or evening, wherever you are in the world. Like she said, my name is Iwinosa Aideyan, but everybody calls me Winnie in the US right now. I'm originally from Nigeria. I'm a third-year PhD student at Clemson, and she has talked about my research areas. So today, I'll be presenting my work on securing the vehicle firmware supply chain through a framework that we call GuixChain in my research lab. So to give you a quick background, this work is a part of a broader project under the VIPR-GS Center here at Clemson University in collaboration with the U.S. Army DEVCOM Ground Vehicle System Center as a part of an ongoing effort to develop the next generation military ground vehicle. This project started officially in the early of 2024, and it focuses on developing a standardized modular secure firmware update framework targeted at military vehicles. But for this research, it's targeted at normal commercial or personal vehicles. So it's divided into two parts. We have the first part led by my advisor, Dr. Brooks, where we focus about securing the vehicle firmware supply chain itself, making sure that what gets built, tested, and shipped is authentic and trustworthy. Then we have the second phase that's focusing on distributing the firmware once it enters the vehicle. So we secure from the developers to the cloud, then from the cloud to the vehicle. Dr. Percy secures the in-vehicle communication security process. So today I'll be presenting my contribution to phase one. As we all know, modern vehicles have become highly complex highly complex software-driven system. We have moved from having mechanical systems to more embedded systems, more electrical units in a vehicle. And these electrical units, these embedded systems, they work on software. They run on software, just like our phones, right? So some vehicles today have over 100 lines of code distributed across over 100 plus ECUs, that's electronic controller units. And with this, we have increased connectivity, which we love. Connectivity between vehicle to vehicle, vehicle to cloud, integration with mobile apps like your navigation in your car. So this connectivity, this expansion, this growth has increased the attack surface. Like it has significantly expanded. So this has led to a rise of successful cybersecurity attacks in the past decade. Like we have seen remote car hijacking, theft using the app vulnerabilities, and various software exploits. So I have some snippets of different headings on my slides. At the same time, we have software updates. Once we find, oh, we have this issue, we have this attack, how do we fix that? We have software updates where we can carry out, we can add a new feature to the vehicle. We could patch an existing security vulnerability, and we also have over-the-air updates. Over time, if you want to carry out an update on your vehicle, you take your car to the dealership, right? And they plug it into the OBD code and you carry out the update. But nowadays, you can just be at home, connect your vehicle to the Wi-Fi and take an app. It will automatically download the software. So we're introduced to over-the-air updates, that's the OTA. Now, the big question is, how can we ensure that the software being developed is secure, authentic, and tamper-proof? That is what this work is trying to address, to ensure the software that left the OEM gets to the vehicle is not changed along that process. Now that we have understood how important software updates has become, let's look at some of the major challenges, like the motivation why we carried out this work. Now, we have seen that vehicles firmware updates, they often come from multiple suppliers and vendors. There are different ECUs in a vehicle made by different suppliers, and we have a very complex supply chain when it comes to the automotive industry. We have the tier 1, the tier 2, the tier 3. Everybody comes together to make a particular vehicle. So the OEMs basically just assemble, but other suppliers make the software and make the units. So at each of these stages, from the source code, from the development team, to the audit and the build process, to the image repository, there is potential for compromise. Even if just one vendor gets compromised, automatically the whole process downstream into the vehicle's OTA update is compromised. So even if vendor A is secure and vendor B is not, they are all going to be in the same car ecosystem. So this distributed nature of the supply chain introduces a wide attack surface. This is where we start to see why a secure supply chain framework is needed. Now, another motivation is we have an existing well-adopted framework, on over-the-air framework called the Obtain framework. As you see here, the to the vehicles using multiple roles, and it includes director repo, the image repo, and the time server. So let me just briefly walk us through the Obtain framework before I say what is wrong. So first, we have the image repo. So image repo is where the firmware finally is stored. Into this cloud, that is the image repo. So it is saved with the cryptographic metadata, like the hashes, the version number of the artifact, the signature, to describe the image itself. So image or artifact or software, they are all the same thing. So if I use image, you know I'm talking about the software. So this image repo holds what, but does not decide who gets what. Now we have the director repository. So the director repository tracks all of the vehicle's software updates for all the ECUs, for all types of car. So it knows what versions are installed on each car. And based on that, it prepares a customized manifest for each vehicle, deciding what update should go to which car. So even if an attacker compromises this repository, it cannot act alone because it still needs to connect to the image repository. Then we have the time server. So the reason why I added it here is like this time server prevents robot attack. The Obtain framework is a very, very good framework. It's very secure. So the time server sends signed tokens to ensure that the updates are still fresh and within the validation period. So without that time token of that current time, the updates will be rejected by the car. Then we have the telematics units or the gateway. That's the ECU in the car that receives the firmware and carries out full verification. And if it checks, it will send it to the appropriate ECU that needs that particular update. So overall, we see that Obtain splits trust between multiple roles, meaning that the attacker will have to compromise several components to succeed. But this is where our work begins. The Obtain assumes that the firmware inside this firmware image inside the image repo is correct and trustworthy. It doesn't address what happens earlier, like the source code, the supplier's repository, the build system, all these changes where the attacker could possibly insert malicious code before the Obtain sees it. Now, this is where our solution called GuixChain comes in. The goal is to strengthen the part of the supply chain before the obtain takes over. We integrate multiple technologies to achieve this. We begin with the Git for version control, where every developer submits their source code, every commit is tracked, every change is tracked. Next, we store the copies of the source code commits on the blockchain ledger. So this just creates an immutable tamper-proof record of all the code changes. Even if someone tries to rewrite the history, the blockchain will have a permanent audit trail. Then inside the blockchain, we have what we call the smart contract. I'll talk about this in details in my comment slide, but just the overview of what GuixChain have. So we have the smart contract that is used to automate the build process. When we are done with the coding, with the testing, we're ready to push the software to the vehicle. Then we get to the reproducible build. Now we are done with the coding or the testing. We want to actually build to convert the source code to the firmware. We have reproducible builds with different identical servers that compile the same source code, and ideally they should give us the same output. Then the output is being compared, and if they're all the same, yes, we'll push it to the obtain repository. Then we have the software bill of materials. Since we are having different source code generating the firmware or the image, the artifacts, we have to have like a list of everything that was used, all the ingredients to bring out of the software. So in this way, the GuixChain closes the upstream gap that the obtain does not address, providing an end-to-end software supply chain security from the source code to the deployed vehicle firmware. Now I'm going to go into each and all these various 4 components. I highlighted Git for version control, I highlighted blockchain, I highlighted software bill of material, SBOMs, and I highlighted reproducible build. So let's analyze version control. Now we know that Git is one of the foundation of any secure software development pipeline. For you to start writing your code, you need an IDE. So people just use Git. So Git allows the team to track changes to the source code. Every change, every modification is adding a new feature, fixing a bug. Everything is recorded in the history to preserve who made what change and when. It has branching and merging capabilities, and importantly, Git provides traceability. We can always review the complete commit history to the audit change. And finally, Git can integrate directly to the CI/CD pipeline. This allows for automated building, testing, deployment of firmware, making the general deployment process much easier. So that's just all about Git for version control. Now, blockchain. Before I explain how we use blockchain in the GuixChain, I have to take a moment to explain blockchain itself. I know when anyone hears blockchain, they think about Bitcoin, but no, blockchain is much more than just cryptocurrency. Blockchain is a shared immutable ledger. It records transactions transparently using cryptography and a decentralized network of computers, which we call nodes. So you have multiple nodes on a network holding the same copy of a ledger. Everybody can see it. So some key characteristics of blockchain is that it is decentralized. We don't have a single person or company controlling it. Every node on the network have responsibility of maintaining the ledger, maintaining the list of transactions. It is immutable. That means no one can try to change any data. Once it is added to the blockchain, there's no going back. It's permanent, it's immutable. You cannot alter it. Then also it's transparent. Since every participant, every node can view the full history of what happened on the network. Another powerful thing about blockchain is the use of smart contracts. So what are smart contracts? Smart contracts are programs that they are self-executing programs that automatically enforce rules and trigger actions when specific preconditions are met. Like you have a blockchain now. Anytime you get $10,000, send this document from Mr. A to Mr. B. So it's automated. You don't need human transaction. So that's the smart contract for us. So in GuixChain, we leverage these blockchain features to not only securely track the software development, but also trigger the build process and the verification steps in the firmware supply chain. Now we can now look at blockchain, how we use it in the GuixChain. So now for every software event, a commit, a code commit, a build event, it's permanently recorded on the blockchain. So everything that is being done from the code is recorded step by step on the blockchain. If anyone tries to change or modify a code or the build results, it will be obvious because of the chain. So we can have multiple suppliers, we can have the OEMs, the tier 1, the tier 2, the auditors, all acting as different nodes participating on this network. So over the years, like research, we have seen that in the automotive industry, some OEMs are already using blockchain, but basically for hardware. So we have BMW with their blockchain solution called the pack chain, which is used to just track all the physical hardware components from its global suppliers. Then we also have Ford, that Ford uses blockchain to verify the ethical sourcing of cobalt for their EV batteries from Congo. So this tracks, was it got from a reliable source? Where is it right now? Is it across the ocean? So these tools, we just show that blockchain is already being applied. It's used in health, logistics, in food, but in automotive, it's used for mainly hardware. So what makes GuixChain different is that we're trying to bring this same level of traceability to the software supply chain, ensuring that every firmware update is not only securely delivered, but also securely built and verified from the very first line of code. Okay, I have to still talk about how did we use smart contracts in GuixChain. So we see that for smart contracts, we use this to ensure that we have all the commits. Anytime we have a Git activity, it will be saved automatically to the blockchain. If we don't want to build automatically to the blockchain, so it's eliminating human transaction. And for this blockchain, we use the Hyperledger Fabric. Hyperledger Fabric is a tool under the IBM Foundation. They gave it to the Linux Foundation too. So why did we use Hyperledger Fabric? So it has a modular architecture that allows us to customize the system based on how we want for our setup. It also supports multiple consensus protocol. So we could pick any protocol that we want to implement during our setup. Then it has a private channel between organizations. That means a tier 1 we want to talk to a particular OEM without the other suppliers knowing. So we have different channels communication on the Hyperledger Fabric. And one final point too was that Hyperledger Fabric has a special feature which you call chain code as a service. So chain code in Hyperledger Fabric is same thing as smart contract. You can run your smart contract independently of your node. So it's a special feature that we actually like. That's why we selected Hyperledger Fabric. In this way, we combine the security of blockchain with the automation of the smart contract to create an highly transparent, tamper-proof, full auditable software supply chain. Now, let's go to the reproducible builds. The third component is reproducible build. So the idea behind this is just very simple. If you have the same source code passed to different independent build environments, they should produce exactly the same binary output, bit for bit identical. It's very simple. So the way we achieve this is by the source code. We remove any form of randomness in the build process, like timestamps, file ordering, any kind of environmental difference. We take it out so that we can make this build deterministic. So why is this important? This is important because it allows us to detect tampering or any kind of insertion of backdoors. Even a single unexpected bit difference can throw it off. All the servers must bring out the same output, ideally. Then finally, we see that it strengthens security across the software supply chain by protecting the build infrastructure. Since we have control of the build infrastructure, it makes the attacks much harder to execute. So we see that this is used in Bitcoin, uses this, the top browser uses this. So many Linux distribution uses reproducible build idea, and even the Android open source project are thinking about trying to adopt reproducible build for integrity. So for this experiment, we used what we call GUIX. So this is where GuixChain comes. This is GUIX. The G is for GUIX for version control. Why GUIX is the G2 is for GUIX for reproducible build. So we see that GUIX emphasizes reproducible build. So if you give it, ideally, if you give it the same source code and the same build environment, GUIX will ensure that we have identical bit for bit output every time. Secondly, GUIX provides a fully transparent build system. Every dependency, every build step, the configuration is managed, declared. Everybody can see how it's being managed. So this makes it easier to audit, reproduce, and verify across all parties. Then it supports cross compilation, because we often build firmware for embedded systems and they run on different kind of architecture. So GUIX has different kinds of environments to build. So you can build real-time OS on the environment. Different kind of OS can be built in this environment. So finally, we see that GUIX can seamlessly integrate with our smart contracts. Smart contracts, they basically run on virtual machines, and we can also create or add GUIX in that same virtual machine. So this was a plus. This was a plus for us. In short, the GUIX gives us full control and transparency, making sure that what we built is exactly what we intended to build and nothing else. Now, the last part of our technologies is software bill of materials. So SBOMs is a formal record of all the components, the libraries, the package, the dependency that was used to build a particular piece of software. So you think about it like your ingredient list in your cereal in your cereal, like a food label. It tells you what is inside, where it came from, and who fit it together. So SBOMs are critical for different kinds of reasons. SBOMs shows us transparency. We can see exactly what is in our firmware, what is in the build. It also offers provenance. We can trace the origin of every included component. Where did this dependency come from? Who made it? Where? Was there any vulnerability tied to it? Has it been patched? Then we also have vulnerability management, which is a big part of the SBOMs. If any vulnerability is discovered in the wild, you can easily use your SBOM to track, do I have this library? Do I have this dependency? And you'll be able to remediate it efficiently. So in GuixChain, SBOM generation is integrated into the reproducible build process. So as your software is being compiled, you're generating the SBOMs of everything that used to make the build or the image. So this is just by the side. One of the things we saw researching about SBOMs is that SBOMs is widely discussed and promoted, especially after the executive order we had in 2021, after the SolarWinds attack. But there are still significant gaps in practice, and there are still gaps in practice, especially in the automotive software. First of all, we tried to see what do we have about automotive SBOMs, and it was really, really hard to see. Like, we don't really have so much literature related to SBOMs for the automotive embedded firmware, but we could see so much on the cloud and different enterprise applications. Secondly, even when SBOMs are generated, they are still limited to actually consume and analyze and exploit SBOMs data. So people just create or generate SBOMs without checking it out, like what it gives us, is it correct, or just a checklist in their complete list of things to do when getting a software. Finally, which is critical also, is that there are really few validation mechanisms to ensure that your SBOM is exactly what it's meant to be. It hasn't been altered. So in GuixChain, in GuixChain, we address this by integrating SBOMs verification directly into the blockchain build process. If the source code are the same, right, that means the SBOM should be the same. So we have a way of verifying that our SBOMs are identical across all nodes, adding an additional layer of integrity check in this process. Now, we are done with so much technologies. Let's go into the real work, the workflow. So first of all, the process starts by the developer working in their IDE, committing the code to their various Git repository. Then once it gets there, the repository communicates with the smart contract, and it sends the information like the Git commit, the author, the hash to the ledger. Now, in the ledger, we could carry out the testing using the smart contract. We carry out verification steps in the smart contract. When we are done with all this, we can now push it to be built, right? Now, the reproducible build happens across different Git servers. So you can have, depending on your company, 10, 25, and they will carry out the compilation in parallel at the same time. And after this, the SBOMs are still in the same process. The SBOMs are still being automatically generated. Then we carry out a bitwise comparison of all the generated build output across all nodes. And if and only if they are the same, one is pushed to the obtained framework. So in this way, the GuixChain creates a fully verifiable, transparent, tamper-proof pipeline, starting from the code all the way to validating the firmware images with the blockchain, ensuring a permanent auditability at each step. Now, this slide just shows like the full integration, showing us how we bring everything together. So we have 3 different stages. We have the Git to blockchain stage. We have the blockchain to reproducible build stage, and we also have the Git to storage stage, where we carry out the consensus, compare all the outputs, and ideally put one in the obtained framework. Now I'm going to talk about the 3 stages and why they are important. So one of our questions we got from the Army during our presentation last year, December, was why integrate Gix with blockchain? Isn't blockchain resource intensive? I'm like, no, because we know about Bitcoin, we think all blockchains are intensive, material or resource intensive. So why? In the traditional use of Git itself, it can allow history rewriting using Git push command or Git rebates. So this can give a way to you can hide malicious changes. It can be hidden in the code. So we see that Git repository can be vulnerable to rollback attacks, ransomware, and even insider manipulation. So the Git gives us a powerful way to manage that by having an immutable ledger transparency. So that's just why we integrated Git to blockchain, and we choose hyperledger fabric, which allows us to pick the consensus that will be less resource intensive. So the key takeaway from this is that GuixChain leverages this integration to ensure that every code change is securely tracked and verified and permanently recorded. Very simple. So this image just shows how we technically wrote the code to link the Git to the blockchain, like how we carry out the transformation using the different certificates. Every developer will have certificates to access the blockchain network. Not anybody can access. Every node, every supplier will have their own ID, will have their own key, will have their own Bitcoin wallet, if you want to use that term. This just showed how we carried out the link. Now, the final part of the Gix to blockchain integration was that we did not want to just assume a particular method. So we tried to see, are there other different ways of integrating Gix to the blockchain? So we saw like we came out with 3 different models. So the first one is independent final clone and commit hash storage. So in this model, we just store the commit metadata, the hash, the author, the messages, the timestamp on the blockchain. Then use the git clone command to automatically clone the code base in all the nodes on the blockchain network. Then 2 is synchronize repository with diff commit. So once a developer is done making a change, he sends the diff file, the delta, to all the nodes, and all the nodes carry out the cloning. And finally, the automated sync with direct push. So in this approach, commits are directly pushed into the blockchain automatically per time. So you change a print statement, automatically every node will change their own statement. So this ensures that all the blockchain nodes have identical and fully synchronized repository at all times. Ultimately, GuixChain supports multiple integration patterns. depending on the deployment needs and security constraints and system scalability requirements. So for this, we carried out an experiment for this, and it's currently undergoing OPSEC review by the Army. So I cannot really talk about this much, but hopefully in summer we'll have it published and everybody can check it out. What we saw, like which of these scenarios would be better for it. So how did we pick one? So we used after we finished designing those 3 scenarios, the question was, how do we evaluate which one was better? That's how we got the answer. So we looked at the synchronization time, the consistency, like does every node have the exact code base at the same time? Do they have the same commit hash? Do they have the same code base? We looked at how well did each model prevent unauthorized changes? Can someone tamper with the node repository without being detected? Then also we looked at the system resource load. We checked out the CPU, the memory, the network usage to ensure that happens during the synchronization verification time. So we have conducted these results, and it has been collected. Hopefully in summer we'll see the answer. The second part is, how did we integrate the blockchain to the GIGs to ensure that we have the same build process all the time? Now, why did we do this? We did it because it will give us multiple outputs with multiple nodes, right? So we can carry out a bit by bit comparison. So both the smart contract and the build system, they run inside the environment. So that can reduce synchronization overhead and eliminate environment drift. So, and having blockchain tied to GIGs is that we can log and maintain all the build processes for from the beginning to the end. So that log, we can use it for compliance also. What was done, how was the environment, and it's stored on the net. So one key takeaway from this merge is that blockchain is that by integrating blockchain with the GIGs, we can have full control over the software environment. This allows us to build for multiple platforms while guaranteeing that every node independently produces identical software artifacts at all times. So one side experiment was to see, do we have the blockchain and the GIGs in the same container or have it in 2 different containers? So we also looked at that. So in summary, okay, so we have to pick between 2 different kinds of trade-off. Do we want to go for simplicity or separation? So running both components together in the same container creates a tightly coupled but much simple development model. Or do you want to separate them for isolation? So we have to think about those 2, but we picked one at the end though. So ultimately, we chose the single container approach for the GuixChain. Now, the last stage for integration is after the GIGs has finished building the artifacts, we have to ensure that they have the same output, right? So this ensures that every node produces the same build output, and it's bit by bit identical. If there's any kind of differences, it's going to be flagged away and rejected. It won't be sent for storage. Now that we have completed this process, what happens next? So we have carried out the build at the same time. We have multiple builds already out. We have the SBOM generated with the softwares. Now we have to carry out what we call an artifact hashing verification. Once the builds are complete, every node will compute cryptographic hashes for its generated artifacts. So we'll have hashes for the SBOMs, hashes for the image itself, hashes for the metadata. So these hashes are then shared across the nodes for the comparison. Now, only if all the nodes have the same the same output, then it is sent to the obtained framework using a secure channel, SSL or TLS encryption for it to get there. So with this final stage, GuixChain ensures that what is built is exactly what gets deployed, providing a trustworthy and auditable chain of custody for the firmware, fully integrated with the obtained infrastructure, like I showed in like slide 2 or slide 3. Now, we have built a secure firmware. That's what we think, right? We have to understand the specific attacks we are trying to defend against. So we looked at build server compromise, we looked at ransomware, we looked at arbitrary edit and insider attacks. So for build server compromise, an attacker can have access to the build system and inject maybe a malicious code or a backdoor directly into the compiled firmware. And trust me, nobody wants that. Then we also have ransomware, whereby the attacker can encrypt the source code repository, and the OEMs or the suppliers can lose access to their firmware, to their source code, which can halt productions, and it can disrupt operations, leaving the vehicles open, leaving the vehicles open for vulnerabilities. Then we have the auditable edits, which just refers to unauthorized or accidental change to the source code or the build environment. The insider attack. We can agree that you cannot ignore insider attack, because a trusted contractor or supplier or vendor can have legitimate access to this to all these processes, and it can just introduce a particular issue or a particular bug to it. So this is kind of the hardest to prevent, because of the actor already has access to the system. But the way we develop GuixChain, the architecture directly addresses these risks by introducing a tamper-proof log. So even though you have access or you change something, we will know who did what and at what time. We will know what was changed. We'll have like a forensic track to see what was changed. So this is just how GuixChain covers or protects us against these threats. So this diagram just gives us which point in the flow does this threats covers. So we see that for one, having the reproducible builds, having many servers carrying out the compilation prevents build server compromise. You have to go into each of the servers to change everything for you to get your malicious firmware to the vehicle, and trust me, that's going to be hard, take a lot of time. For two, ransomware, because we have multiple nodes on the network, you cannot corrupt all the nodes on the network. It's kind of going to be impossible. So we have redundancy thanks to blockchain and the Git also. Then for three, arbitrary edit, because of the log and the way the smart contract works, anything that is being done on the code is being sent, is being stored on the ledger. And if it's not consistent, it won't be pushed for building. It won't be pushed for building. It will never get to the obtained image repo. And the last thing is insider attack. Insider attack can be caught from the ledger, like who changed what. It can also be caught in the reproducible build. If the insider attacker just fixed one thing on one build server and one is wrong, it will not compile, it will not have a successful verification process, and it wouldn't get to the obtained framework. Now that we have seen the core design and how GuixChain addresses the security threats, let's just try and see where are we going next in my research lab. So first of all, we have all these separate stages already fully working independently. So the next step for us is for us to integrate these stages into one unified system and see how it will work together. The other thing too is that in the comparison part, I was saying if and only if they are the same. Well, we're thinking, how can we have a more comprehensive comparison algorithm? Do we do a 3/3 of the network? If 75% are correct, push that image to the storage, or 50%? So we're thinking about what consensus do we use in that aspect. So that's what we're working on back end. Then the last one is when we are done with all these changes, we're trying to see how we could submit a paper about the GuixChain into the ACM DLC research and practice special edition of trusted Internet of Vehicles. This will allow us to share our results and framework design to a broader research audience and invite for future collaboration. We would love to carry out this with a real life test bed, having the obtained working at ECU, having the full process. So we really want to carry out that. In summary, we have established a very strong foundation, and we're actively looking for a way to advance it with full system integration and real-world scalability. Now, the last part of it. In conclusion, I have been able to show that GuixChain can create a trusted foundation for securing automotive software supply chain by combining blockchain, its immutability, GUIX for its transparency, GUIX for reproducible build, SBOMs for a list of all the components used for building, and also riding on the obtained secure over-the-air delivery method. And we saw that it's able to mitigate between insider attacks, ransomware, build server compromise. So in all, we think that GuixChain will be able to offer a trustworthy blueprint for the future of the automotive software integrity. So with this, I will say a big thank you to the ASWRG women for having me today, and also my advisor. Thank you for letting me present my work. I really appreciate everybody that is here.